Hello, everyone. Welcome to Forest Learn. My name is Suva. You may recognize my voice from the videos on the channel. I'm really excited to launch a new series of videos where I interview people who either work in physics or studied physics and have now moved into a different field. Hopefully, these interviews will be interesting, useful, and inspiring even for those of you contemplating studying physics at uni and beyond, and perhaps thinking about the sort of career paths open to one after studying physics. So I'm really, really happy to be joined for this first interview by my friend and ex-collaborator, James de Lisle. James and I met as PhD students at the University of Leeds, where we worked in the research group of Professor Yanis Pakos, who I hope to interview soon. I have some great memories of the research we did together, which led to a paper being published, along with some fun times outside of work. Today, James is working as a machine learning engineer at the startup Adarga, which is doing some very interesting work. I'll leave a link in the description below for those of you who want to learn more about Adarga. So, without further ado, welcome, James. Thanks for joining me and agreeing to share your experiences and insights.
Well, thanks for having me. Fun times.
Pleasure. So, James, can you tell us when and how you first became interested in physics?
Yeah, I mean, for me, it might be a bit of perhaps a cliche almost. Like for me, it was very much a teacher that did it for me. When I was in primary school, I had a science teacher, because of course it's all general science back then, whose name was Mr. Bull. I actually dedicated my PhD thesis to him.
Oh, right. Wow.
He was just a really fantastic teacher. I think perhaps I had some predisposition to it. I don't know what the nature versus nurture argument is these days, where it falls, but certainly I feel if I hadn't had Mr. Bull as a teacher, so enabling me to pursue those interests in like a really positive and proactive way, then I perhaps would have gone down a very different path in life. It was just, yeah, like, I guess, I don't know whether it was his specific style. I don't think it was that I had access, or he had access to more resources or anything than a typical teacher. And maybe, I've only had him as my science teacher at that age, so I can't compare to other science teachers, but really, like, I was even, and this isn't because I'm some sort of child prodigy by any stretch of the imagination, but like having access to things like, working on like electric circuits and you have the base stuff that you're allowed to, that's on the syllabus when you're that age, plugging in bulbs and cells and stuff and connecting it all up. But, I really enjoyed that. And he was, there to take, from the baseline level and extend it, as far as I wanted to go at that point. And that's just one example of where, he really sort of allowed students to achieve, whatever potential they wanted at that stage. That's really where I first became really interested in it.
Wow, that's really interesting to hear that you were inspired and nurtured by someone at such a relatively young age. That's great. So why did you decide to study maths and physics at university?
So, I mean, as I just said, like at a very young age, it was very much my subject, physics, much more so than maths, actually. I only really started to excel at maths at kind of GCSE level. Prior to that, it had been, something which I was okay at, but not particularly great. But, physics was, when you go and do all of your assessments, it was like, oh yeah, James has done really well in physics and terrible in English. So that's definitely a contributing factor. I don't think I was ever thinking at the stage where I was deciding to go to university to do whatever it was going to be, that, physics was a particularly good degree to have for professional sort of reasons, which it is, as I'm sure we'll come on to.
Yeah.
But at that point, it was just, this is what I'm great at and what I'm really interested in. As to why I did maths and physics joint honours, as opposed to, say, straight physics, I guess, as I said, like at GCSE level was when I really kind of started to understand maths, what maths was beyond, quadratic equations and plotting, functions on a graph.
Yeah.
Understanding algebra and calculus and all of these other things which feed into physics. And I suspect that it was because until you get to A-level maths, you don't do things like calculus. And calculus and like things like calculus and like higher order mathematics dovetails so well with physics that I think once we started doing those kind of more advanced topics in maths, I realized that it related much more to things which I felt much more intuitively comfortable with, which was physics. And so that sort of it acted as a kind of accelerant for both. And so, I definitely, it was a choice between maths and physics as opposed to theoretical physics, which was another degree in, so the theoretical physics was entirely in the physics department. And, was basically all of the modules were taught by physics lecturers. Mm-hmm. But the maths physics course just provided me, I was never really into experimental physics at that stage. And so I wanted to do as little experimental as possible, then the maths physics joint honours was the way to do that.
We shared some things in common even from such a relatively early stage. Right. Yeah. Okay. Interesting. So yeah, that interplay between maths and physics is what really kind of got you to.
Yeah, I'd say so. Although I think retrospectively, the course at Bristol where I did it, there was I think a lot more could have been done to integrate the two courses and maybe be a bit more complementary. Like a lot of the units I did, they were really interesting. And to be honest, I wouldn't change it because I ended up learning some maths that I never would have done had it been much more kind of integrated, focused. Yeah. But, for example, I think I came to the end of my bachelor's degree and I'd never studied Bessel functions, for example, or something which is typically very much like taught in physics courses. But yes, that's another story.
I mean, you probably knew about as much about Bessel functions as me, despite me actually having learned about Bessel functions. But anyway, so okay, you've talked a little bit about your experience of studying at the University of Bristol, and of course, there's many dimensions to talking about, the experience of studying at university. Let's just stick to the academic side of things. And yeah, let's maybe break it up into three separate questions. So first up, kind of what was the step up from A-levels like
for you? For me, so for my A-levels, I did chemistry, physics, maths, and further maths. Mm-hmm. So that really gave me a leg up. Certainly the further maths did. It allowed me to study concepts which basically the entire of the first year of undergraduate physics, the mathematical components were I'd already done, and there was very little effort involved there. I mean, obviously the maths component of my degree, like the maths side of the joint honours, I think we covered the entire up to further maths in the first 2 months of the course, of the first year course, and then you move on to new stuff. But certainly for the physics, it was. I found the maths not challenging at all, and because I was doing the joint honours, and you always are. The maths component of it is always well ahead and more advanced than the maths in the physics component. I never really found any of the maths in the physics side of my course challenging for that reason. I started with a head start, and then the maths was always ahead of it. The maths side of the course, I found certainly the pure maths component of the course I found quite difficult at first. It was something that I think I don't know whether it's still in the A-level syllabus, further maths syllabus, but in P6, I think it's called P3 now because it goes C1 to 4 and then P1 to I can't remember how it goes, but one of the advanced pure modules in A-level, you do proofs proof by contradiction, proof by induction, but it's very limited. And then suddenly you're at university and they're like, we need you to prove by induction that this series converges to, blah, blah, blah. And you're just like, I found it's changing the mode of thinking, in the same way that when you go to GCSE to A-level maths and physics, less so physics, but you've got to change the way not just like what you're thinking about, but how you think about it. And it's the same again at university. It's quite a big step up. And I think quite a lot of people struggle. Most people manages to achieve that change, but I certainly found it difficult. I guess to comment on the physics side of things, in the first year of physics, it's a lot of core modules. It's a lot of relearning stuff that you learnt at A level, but with maths attached to it. It's right. Like taking mechanics, which, when you're in A level, at least when I did A level, it's like F equals ma. Let's calculate. There's not a huge amount of. Whereas, when you start mechanics in undergraduate first year, it's like, okay, let's construct a differential equation for this physical system, and then let's solve it. And then, and it's changing the approach to things that you've done before. But as I said, like that, because I had the maths advantage with the further maths to start with, it never really was a great struggle.
Right. Yeah. No, I can attest to the fact that having studied further maths, it really helps with the step up to studying physics. So what would you say is the most challenging thing you studied or faced in your degree?
I think probably it was, the two things. I guess there was the more kind of abstract problem of just really struggling to get certain concepts. When I was at A level, it was certain parts of it were difficult, but it was always felt like it was kind of achievable because it's A level. Everybody does A levels, and so they're not going to make it so difficult that I can't, sit down for an hour or two and like really understand it to the extent that I need. Whereas when I was doing my undergraduate, certainly at the beginning and also towards the end when I was in my final years and doing some of the more advanced modules, there's moments where I'm just sitting there and I've been bashing my head for hours and hours and I just cannot fathom it. It's a deeply humbling, but also deeply frustrating experience.
Right.
But having said that, there are, as I'm sure we'll talk about in a minute, like the corresponding conjugate of that is great positives. But I guess in terms of specific thing that I learned, probably I found general relativity quite difficult to grasp. It relies on some pretty heavy maths, which I'll actually mention again in a moment, like the concept of like differential geometry, which you do in a very limited capacity when you're studying it in an undergraduate physics context. But when you're first getting to grips with that is again another mode of thinking. It's constantly transforming the way you think.
I can totally second general relativity being one of the hardest things that I faced studying for my physics degree as well. And just for our viewers, general relativity is one of Einstein's, perhaps the crowning achievement of kind of out of all of Einstein's contributions to theoretical physics or physics in general. And yeah, it's a tough one. It's a tough one to get your head around as an undergrad. So yeah, would you say general relativity was one of your favorite or most memorable things you studied, despite it being really hard?
I'd say so. Yeah, that's correct. I mean, it's so as I said, like, general relativity is, as Siva said, the sort of theory of gravity that Einstein came up with, his crowning achievement. But the mathematics, the kind of core mathematical theory that underlies it is something called differential geometry, which is a kind of a form of calculus that's a kind of a bit more general, perhaps a bit more abstract. And I studied general relativity in the physics department in my third year, I guess it would have been. But I also studied differential geometry as a separate subject in the maths department at the same time. Mm-hmm. And I found that as much as general relativity was very difficult, I found differential geometry was hard, but more rewarding. Because I think they with the in general relativity in physics, you're being presented with a kind of a reduced version of the core mathematical principles, because they have to do that to be able to present the concepts. Whereas in differential geometry, it was the same topic fundamentally, but presented from a ground up constructivist way that was, I just found much more not relatable, but comprehensible in some capacity.
More satisfying intellectually, I guess.
I guess so. Yeah, that's right. And it was, it's just, as we'll come to in a moment, like it's one of the underpinning principles of what I studied in my PhD, and it's a whole, in the same way that learning calculus and understanding like classical mechanics in terms of calculus is like a transformation in your understanding of how physics works from A level to undergraduate. I found differential geometry was, again, another kind of transformative thing to know and have understanding about that allows you to view things that you had previously understood in one way in a completely different way. Just deeply satisfying.
Yeah. So after graduating, you trained as a teacher and you taught for a couple of years. And after that, you attended the University of Leeds, where you obtained the Masters in Quantum Technologies and a PhD in the Quantum Information Group, which is where we met. So what motivated you to get back into education and obtain your Masters and PhD degrees?
So I stepped out of academia, as you said, to do teacher training in secondary physics. And I had always intended, I think, to come back to academia. My teaching was always an interlude. I gained a lot from it. I improved my work ethic quite a bit, I think, in that period. But yeah, it had always been my intention, I think, to come back. As I said, I was into physics from a very young age, and I only got more into it as I went through education. It's, yeah, I think that's my answer. I'd always intended to come back, and I did.
Okay, interesting. So this next question might be a bit of a challenge for you. So in very basic terms, can you describe the research that you carried out for your PhD? And
okay, I'm going to give this my best shot.
But just be gentle on our viewers here.
Of course.
Be mindful.
So basically, there's a big push at the moment to build what's termed a quantum computer. Now, I'm not going to try and explain what a quantum computer is, but
that's for another time. Yeah.
it's a new type of way of thinking about doing calculations, and you can build a device that can theoretically do things quicker in certain contexts than a normal computer like the one that we're using to record this conversation. However, there's a problem with the theory or like the practice of implementing these kind of ideas in reality, and that's that the kind of physical systems that support this new interesting type of physics and computation are very fragile, like very fragile. And so what we need to do in order to be able to implement them in reality and actually do stuff with them is design them in such a way that they're robust, like that we can store information in them in a very, what we call, fault tolerant way. And so the way that the people in my field, our field, thought to do this was to borrow from mathematics, specifically a field called topology, which basically says that certain things have certain properties that stay the same, even if you change that thing quite a bit. So an example is a rubber band, right? A rubber band is just a loop of rubber. And that loop has a hole in the middle, right? It's just like, you can think of it as one hole. However, and I can twist my rubber band, and I can stretch it, and I can tie it in knots. But no matter what you do to it, you can always say that there's got one hole in the middle. And that's the core underlying principle that we try to use to store information in these physical systems in a way that was sort of the twisting and the bending of the rubber band corresponds to the kind of outside influences that you might have, like radiation, light, heat, all these sorts of things that might disturb our very fragile system. So we redesigned the system to store information in as effectively as loops, right? As our rubber band. So we can say, okay, if our rubber band has one hole, then it's one thing. And if it's got two holes, then it's another thing. And even if our rubber bands get twisted around, whatever it may be, as long as we can see that they've got one hole or two hole, then our information is there. So that's a very kind of, I guess, abstract way of viewing what we were doing, I think.
Oh, that's a very nice description. I might leave a link more about topological quantum computation if anybody's interested to learn more about it. So what Jaden's described is a very basic overview of it, but it's a very, very interesting field. So we could spend the whole interview talking about the experience of you doing your PhD, and of course we can't do that. But if you had to choose just 3 words to describe your PhD experience, what would they be?
Oh goodness!
Really slipping hard, right?
Really hard. I would say probably. I'm going to use perhaps a slightly cheesy one, but fulfilling. Like, it was a fulfilling experience overall. You know, when I finished my PhD, I was really proud. You know, with what I'd done. You know, it was a great. I felt So that's definitely one.
So fulfilling. Okay. What 2 other words? It can't have been fulfilling all the way through, right?
No. I was going to say the. I would also say. I mean, I don't want to use, we don't want to go into it too much, but the concept of imposter syndrome, which is this idea that you are surrounded by so many very smart people, and it's quite easy to feel like you don't belong. And so I think probably quite, I guess, humbling is another word I'd use. Not only for the interactions with other people, but also just, realizing how little you do know. That's a big part of it. So humbling. I guess the third word would be just interesting. Really interesting. You spend days, hours, months just reading. I mean, at the time, it can seem perhaps sometimes quite dull, like reading paper after paper, trying to find, whatever it may be. Or running your simulations, to the nth time, and all of these sorts of things. But fundamentally, it's just fascinating. Like, the work I do now is interesting in its own way. But I think back with deep nostalgia at the kind of, the fundamental nature of the work that you do in a physics PhD. Certainly, in the kind of PhDs that we did, and that's not something that you can really find outside of that particular thing.
No, I completely agree. I look back on my experiences with nostalgia as well. I think we're very lucky to, have the chance to do what we did. Go on. Sorry.
I just say fulfilling, humbling, and interesting.
Yeah, those are three great words to describe the experience. Cool. So, after your PhD, you worked as a postdoctoral researcher for a couple of years in Japan. After which you returned to the UK to work as a software engineer, right?
Yeah.
So how helpful was your physics training or background in landing and doing well in your role as a developer?
So I did quite a bit of programming during my PhD, doing numerical simulations for the work that we did. And that was definitely incredibly helpful. I mean, you probably could land a job off the back of a PhD in software engineering if you didn't have that much software experience, but having had so much was a great benefit. Obviously, software engineering is about much more than just programming. It's about understanding software architecture. It's about understanding, well, these days, agile development practices, the concept of testable code, and just things that aren't in any way included in a in a research capacity. Like, I never wrote a single test in the 3.5 years when I was writing code during my research days. But it's just a core component of being a software engineer in a commercial capacity. But having said that, those things are easy to learn. What isn't easy to learn is the skills that studying physics and also, as an added bonus, doing a PhD give you, which is solid mathematical skills and an ability to be able to pass new concepts and implement them in a reasonable amount of time. Which is why they're so why people with physics degrees and PhDs are so valued in so many industries, because of that ability, like that demonstrable ability to be able to take abstract, complicated ideas and convert them into a practical thing that you can actually do or use.
Mm-hmm.
So yeah.
So as I mentioned in the intro, presently you're working as a machine learning engineer at the startup Adarga. And I think there's this perception that to enter the field of machine learning or AI, one needs to study computer science at university. Could you comment on some of the advantages you may have in working in machine learning compared to someone with a traditional comp sci or computer science background?
Yeah, I'd say actually it's probably the opposite. I'd say people with physics degrees have more of an advantage. Maybe not perceptually in terms of getting a job, but certainly in terms of being able to implement and actually produce high quality output.
Wait, you mean physicists are better at programming than computer science graduates?
No, I'm sorry. I'm trying to say that physicists, machine learning isn't about programming.
Yeah, no, of course, yeah, go on.
Machine learning is well, it's a very broad term that includes a wide number of things, but in its most popular incarnation used in industry, the programming is done in Python and it's script based. It's you don't need to be able to understand design patterns or testable code or any of these things. What you need to be able to understand, even then, you don't actually need a huge amount of mathematical ability to be able to just out of the box build a neural network, because the libraries that people have created these days are so usable. But to do good work, you need to understand statistics. That's the core underlying concept. Statistics and a bit of analysis. So that's the study of functions in general, mathematical functions. And a good computer science degree will give you a good basis in mathematical sort of concepts. But in my experience, computer science degrees, it's an afterthought. It's something that they do because you need a bare minimum to be able to understand some principles in algorithmic design and whatnot. Although it depends on the sort of direction you pursue in the computer science degree. But with physics, it's built in from the ground up. I never once studied the statistics required for machine learning during the course of my degree. But as soon as I opened a book to try and understand about machine learning, I skipped the first 5 chapters because it's all just statistics, which you learn as a part of the course when you're doing a physics degree. So I'd say it was incredibly valuable. In fact, most of the people, not most, but a significant proportion of the people who I've met doing work in industry in machine learning have physics degrees.
Right. Well, that says something, right? So yeah, you kind of touched on the next thing I'm going to ask, but I'll ask it anyway. So what kind of advice would you give to someone who likes physics but doesn't know if studying it at uni is the right thing for them? Perhaps they might be unsure about their career path or prospects after uni.
I would say that if you like physics, then you're in a great position because, having a physics degree is, we might come on to this in a moment, but for me, having a physics degree, being great, hugely employable after my degree was a great bonus and benefit, and that was fantastic. And it's great that I get to do interesting work on the back of that. But what physics gave me, doing a physics degree gave me, was just a mode of thinking, a way of viewing the world that is just not only good from a professional perspective, but it was also just, it makes me happy to view, like, I don't know how to describe it. Like, maybe it's you, you've experienced something similar, but like,
Yeah.
it's just, it, you know, maybe obviously, you know, I can't know how other people view the world, and maybe they live an even more like satisfying life than I do. But it's just being able to, it's the kind of skills that you learn allow you to be able to view things in quite a controlled and understandable way. It takes things that I think some people find quite distressing in life, and allows you to maybe not understand them, but at least quantify the uncertainty in a way which allows you to feel a bit better about things. You know, it's, I guess what I'm trying to say is that you should, you know, not only like is physics a super great career path, it's also like a great way to view the world, and therefore, unless you're, if you like physics but also you want to become an artist, right? I mean, well, theoretically, you could do a physics degree and then go and become an artist. I'm trying to think, maybe a doctor, a medical doctor, right? Say if you really love physics, but also you kind of want to be a medical doctor, then perhaps go and study medicine rather than physics. Although you can do medical conversion degrees, so you know.
Yeah, and there's quite a bit of physics in medicine anyway, so there's overlap between the two fields anyway. Yeah.
I guess what, yeah,
go
there's definitely, you know, there's definitely examples where you probably want to go and study something other than physics, but in a lot of cases, I would say that whatever you want to do after university, physics is gonna provide you with like a real solid foundation.
No, totally agree. Yeah. So 2 questions to finish up. First, what's the most mind-blowing idea you've encountered in physics? And please keep it simple. I have no idea what you're gonna say, but let's keep it simple.
Goodness, the most mind-blowing idea. I'd say it's probably related to what we did our PhDs in. It's this idea that, like the analogy I gave earlier about, you know, about rubber bands and that was, I mentioned that it's related to topology, and the mind blowing thing for me is the idea, and it translates to a load of other different areas of physics as well, similar kind of patterns, but it's this notion that like we can sit down and I can write down, you know, define like what does it mean to have a topology or be a particular topological thing, and in a very abstract, pure math way, right? And I can just represent it by some algebra, whatever it may be, and that's that, right? I can just put it away and never think about it again. But the fact that these very abstract, very simple patterns actually occur in physical systems that are like crazy, dirty, complicated, messy, like mushes of electrons and protons, and just, you know, just something that just seems like you could never have any kind of order or like meaning in there other than just like it's matter doing stuff. The fact that these patterns, these very abstract, very pure patterns do appear is like, it's just, it's mind blowing. Like it really is mind blowing. And like, I think some people would say like black holes are mind blowing, or like, you know, whatever it may be, like these huge cosmic things that you can't, you know, string theory is mind blowing. But the fact that, you know, the kind of materials that we were dealing with in our PhD are like a lump of metal that's just on the desk. And yeah, it's real cold, but fundamentally it's just a lump, like when you look at it. But
it's just a dirty, squalid bit of material, right? Which on the face of it doesn't look special, right? And yet it's described by this very, very beautiful mathematics and might underpin some very advanced technologies in the future, right?
Exactly.
Yeah, it is very mind-blowing, yeah.
Staggering.
And finally, you kind of touched on this already, but what does physics mean to you?
Yeah, yes, you're right. I have touched on it already, but I guess to just reiterate the point, I don't know. It's like it's very much part of my identity. You know, I found leaving academia to be very difficult because, you know, it does become kind of a part of you in some sense. Not only just from like an identity perspective, but also just the way you like, the sort of cycles of your brain, the sort of static state of it. Just it's not like I'm seeing numbers or anything like that.
You're having dreams about physics.
Well, that did happen during the peak or perhaps troughs of the PhD, but it's just it's I think it helps you be a better, certainly it helps you be a better citizen, like understanding statistics that underpin policy. It helps me understand, if I'm doing DIY, just being able to like comprehend like basic mechanics, or like perhaps not so basic mechanics. It just never seems to be a moment where I'm like, oh, okay, that's actually relevant and useful and implementable. And yeah, I feel like I'm just kind of inextricably entwined with it, and just who I am, really.
Right. No, that's beautiful. Well, James, thank you so much again for your for taking the time to join me for this interview and sharing your insights and experiences. Yeah, I'm sure our viewers would have found it very useful. So thanks.
Well, thanks a lot, Super. It's been real nice.
It's been my pleasure. And to our viewers, thank you for watching. And remember to give this video a like if you enjoyed watching it, and subscribe to the channel, of course, if you haven't already. Take care, and I hope to see you soon. Bye.
Bye.